Welcome to the module Exporting to FEA. In this module, you will learn how to export loads and results from SolidWorks Motion to SolidWorks Simulation. You will also learn how to run a finite element simulation and obtain stress, displacements, and factor of safety plots in SolidWorks Motion as well as in SolidWorks Simulation. In this module, you will learn how to export loads from SolidWorks Motion to SolidWorks Simulation. Along with that, you will learn how to create and apply action-only moments, edit mates, and specify load-bearing faces. You will also learn how to run structural analysis in SolidWorks Simulation and in SolidWorks Motion. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. A drive shaft is a mechanical component used to transfer torque and power between components that are separated by some distance. In the present case study, we will analyze the drive shaft assembly composed of 5 subassemblies and 2 single parts. The drive shaft is required to transmit a torque of 15 million Newton millimeters at a speed of 2800 RPM. You will determine the stress and deflection of the part journal Cross 1 throughout its rotation by performing an FEA study. Let's see how to apply action-only torque, set up a motion study, solve it, and plot the results. Click Show Me to launch a demonstration video. We have opened the file entitled Drive Shaft Assembly. Make sure that the document units are set to millimeters, grams, seconds. Rename Motion Study 1 to Drive Shaft. Set the type of study to Motion Analysis. Now, we will add a rotary motor. Click Motor. Ensure that the motor type is set to Rotary Motor. Select the input shaft. For motion type, ensure that constant speed is selected. Change the constant speed value to 2800 RPM. Observe the direction of rotation. It doesn't matter which direction it turns as long as we know the direction so that we can add the action-only moment in the opposite direction in the next step. Click OK. Click Force. We will now apply an action-only torque on the output shaft. This is a torque that opposes the rotation, so set the direction opposite the motor added in the previous step. Under Type, click Torque. Ensure that Action Only is selected as direction. Select the output shaft and scroll down. For force function, ensure that constant is selected. Enter a value of 15 million Newton millimeters for the torque. Click OK. The runtime has been set to 0.05 seconds. This is a short runtime but will allow the drive shaft to rotate a little over 2 times. Now, we will change the frames per second value to 2000. Click Motion Study Properties. Specify 2000 frames per second. This will give us 101 frames. Click OK. Now, we will run the study. Click Calculate. Click No to complete the simulation with the current settings. Let's check the degrees of freedom of the motion study. Scroll down. Right-click the Mates folder. Click Degrees of Freedom. We can see that there are 0 degrees of freedom, so we have a kinematic system. Expand the Mates folder. This assembly has 0 degrees of freedom because of the way it was built. If you examine the individual mates, many of them are point-to-point or point-to-line to avoid removing too many degrees of freedom. Close the degrees of freedom dialog. Let's create plots of the angular velocity for the input shaft. Click Results and Plots. Define the plot using displacement, velocity, acceleration, angular velocity, and magnitude. Select the face of the input shaft. Click OK. We can see that the input shaft is turning at 16,800 degrees per second, that is 2,800 RPM, which is the input speed. We will now create a plot of the angular velocity for the output shaft. Click Results and Plots. Define the plot using displacement, velocity, acceleration, angular velocity, and magnitude. Select the face of the output shaft. Click OK. For output shaft also, the angular velocity is 16,800 degrees per second, which is similar to the input speed. Let's create a plot of the angular velocity of the drive shaft. The drive shaft should not rotate at a constant rate. Click Results and Plots. Define the plot using displacement, velocity, acceleration, angular velocity, and magnitude. Select the face of the drive shaft. Click OK. We can see the expected variation of the velocity caused by the offset angle between the input and output. Now, we will create a plot of the torque of the input rotary motor. Click Results and Plots. Define the plot using forces, motor torque, and magnitude. Scroll up and select the rotary motor from the motion tree. Click Rotary Motor 1. Click OK. This is the torque required by the motor to move the shaft at a constant rate. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about applying action-only torque, setting up a motion study, solving it, and plotting the results. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Load-bearing faces are the faces of a component on which loads are applied. For simple mates that include only points or edges, we need to define the load-bearing faces. We can add load-bearing faces for such mates using the Analysis tab of the Mate Property Manager. Any faces involved in the definition of a mate are treated as a load-bearing face in SolidWorks. The Isolate Components button in the Component Display section is used to isolate the components related with that particular mate. Motion simulation allows us to apply the loads and solve the deformation analysis using two distinct methods. The first method is export of the loads into SolidWorks simulation, in which the deformation solution is performed using the SolidWorks simulation interface. The second method is direct solution, where the setup, solution, and the post-processing is performed directly in the motion simulation interface. Let's see how to add load-bearing faces and export loads from SolidWorks Motion to SolidWorks Simulation. Click Show Me to launch a demonstration video. In the Feature Manager design tree, right-click Journal Cross 1 and click Isolate. We are interested in computing the stresses and displacements of this part. Expand the feature tree of the isolated part, Journal Cross 1. Expand the Mates folder. Examine the four mates of this part. None of the mating entities are faces, but rather points or axes. This will require us to specify the faces where the forces will be transferred for each of these four mates. Click Exit Isolate. Let's specify the load-bearing faces for each mate. Right-click the first mate, Coincident 24. Click Edit Feature. Switch to the Analysis tab and scroll down. Click Load-Bearing Faces and then scroll down. Click Isolate Components. This will hide all components except those associated with this mate. Select the exterior cylindrical surface of the journal cross. Then, select the internal cylindrical surface of the universal bearing. To select it, right-click the outer cylindrical surface. Then, click Select Other. Click the first face from the list. Because the faces are touching, Treat as Bonded if Touching is automatically selected. Clear Treat as Bonded if Touching. A bonded connection is one in which the two parts would not be allowed to separate. This is not the case here. Click OK. Click Exit Isolate. We will follow the same process to define the load-bearing faces for the remaining three mates, Coincident 25, Coincident 26, and Coincident 28. We have zoomed out the drive shaft assembly. The load-bearing faces for the remaining three mates have been defined. Now, we need to recalculate the study. Click Calculate. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about exporting loads from SolidWorks Motion to SolidWorks Simulation. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Let's see how to perform stress analysis in SolidWorks simulation. Click Show Me to launch a demonstration video. When an analysis is performed in SolidWorks simulation, the motion loads must first be exported to the part. Ensure that SolidWorks simulation is added inside SolidWorks. Click Simulation. Click Import Motion Loads. Ensure that drive shaft has been selected as the motion study. Select Journal Cross 1 in the Available Assembly Components list. And then click the Add button to move it to the selected components list. Only parts of an assembly are listed here. Parts that are in sub-assemblies will not show in this list. Then, click Multiple Frame Study. This will allow us to specify a range of frames for our analysis. In the Start Frame box, enter 80. Since we have a total of 101 frames, retain the current value in the End box. Click OK. This will import and save the load data to the Journal Cross 1 part and define the design study. These specifications define a design study with 22 sets. Each set has its loads defined from the motion loads developed at the time instant of the frame associated with that set. Let's open the Journal Cross 1 part in its own window. Scroll down. And right-click Journal Cross 1. Click Open Part. A new static study has been added. The numbers 80, 101, and 1 in the study name refer to the starting and ending frame numbers and the frame increment respectively. A design study has also been created. The design study will make use of the static study in order to calculate each of the scenarios. Within the static study, the part must have material defined to it in order for the simulation to run. Switch to the newly created static study. Right-click Journal Cross. Click Apply Edit Material. Ensure that alloy steel from the SolidWorks Materials Library files is selected. Click Apply. And then click Close. We will now create a mesh for the analysis. A mesh is a collection of simple shapes that represent the part. Stress and strain can be calculated within these shapes, and when we define the mesh, we are essentially specifying the size of the mesh elements used. Right-click Mesh in the simulation tree. And click Create Mesh. Click Mesh Parameters. And then click Curvature-Based Mesh. Set the maximum element size to 30 mm. Make sure minimum element size is 6 mm. Click the Mesh Quality tab and then click Journal Cross. Click Apply Draft Mesh Quality. Then click OK, and the model will mesh with Draft Quality Curvature-Based Mesh. Right-click the study in the simulation tree. And click Properties. Because this part is self-equilibrated, use Inertial Relief is selected by default. This option is often used when the analysis requires additional stability. Click OK. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about performing stress analysis in SolidWorks simulation. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Let's proceed with completing the stress analysis in SolidWorks simulation. Click Show Me to launch a demonstration video. Switch to the Design Study tab. The Design Study will make use of the static analysis for each frame calculated. Click Run. Different sets of data will be solved sequentially. Now, we will plot the global maximum for von Mises stress for all the scenarios. In the Design Study tree, right-click Results and Graphs. Click Define Design History Graph. Click Constraint for the y-axis. And ensure that von Mises stress is selected. Click OK. The graph shows the variation of the maximum von Mises stress in the journal X1 part across all the scenarios. We can observe that the largest value of 452 megapascals reached in scenario 1 is less than the yield strength of the material, 620.4 megapascals. This indicates that our design is safe from permanent deformation. Close the graph. Create a similar graph showing the global maximum of the resultant displacements. To do so, right-click Results and Graphs. Then, click Define Design History Graph. Click Constraint. Select Resultant Displacement. Click OK. You can see that the maximum displacement is 0.116 millimeters. Close the graph. In the Design Study, click the column corresponding to Scenario 1 to access the results. Under Results and Graphs, double-click the von Mises stress plot. The maximum von Mises stress magnitude in scenario number 1 is 452.6 megapascals. This verifies what we noted in the design history graph, and it also provides context for where the maximum stress is located. Double-click Resultant Displacement. The maximum resultant displacement in scenario 1 is 0.116 millimeters. Click Save. And close the Journal Cross Part file. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about performing stress analysis in SolidWorks simulation. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. Let's see how to perform stress analysis directly in SolidWorks Motion. Click Show Me to launch a demonstration video. In the Drive Shaft Assembly Motion study, click Simulation Setup. Expand Drive Shaft Assembly. Select Journal Cross 1 and scroll down. Specify 0.0395 seconds for the simulation start time. Ensure that the simulation end time value is 0.05 seconds. Click Add Time to add the time range to the simulation time steps and time ranges field. Click Advanced. And move the mesh slider to set the mesh density scale factor to 0.95 to generate finer mesh. It should be noted that there are fewer mesh controls when performing an FEA analysis within a motion study. Obtaining a mesh which accurately represents a part is a critical aspect of a simulation. Click OK. Click Yes to assign the material to the part. Select Alloy Steel. Click Apply. And then click Close. To solve the finite element simulation, click Calculate Simulation Results. Click Yes to the warning message. SolidWorks displays a message that the playback speed settings for the motion study will result in poor performance and asks if you would like these settings adjusted for better playback. Click No. The timeline has been moved to 0.045 seconds to show the results plot. Set the Results Plot button to show the von Mises stress plot. To do so, click Results Plot and select Stress Plot. The legend indicates a maximum stress of approximately 383 megapascals. However, because Journal Cross 1 is shown in the context of the whole assembly, the stress contours are not easily visible. In this case, a clearer plot will be provided when we isolate the part. To isolate the part, right-click Journal Cross 1 and click Isolate to isolate the part. The stress contours are now visible. The indicated maximum of 383 megapascals is below the yield strength of the material, 620.4 megapascals. The difference in results from this simulation to the last is due to the differences between the mesh. Similarly, we will plot factor of safety. Click Results Plot and select Factor of Safety Plot. The factor of safety is a comparison of the stress seen in the model to the maximum amount of stress the material can experience before permanent deformation. The minimum factor of safety indicated in the plot is 1.62. 620.4 divided by 383 equals 1.62. This means that the part can carry 1.62 times the current load and still not deform permanently. Now, in a similar manner, we will plot a deformation plot at 0.045 seconds. The deformation plot has been plotted at 0.045 seconds. The maximum resultant displacement at time 0.045 seconds is 0.1148 millimeters. The timeline has been moved to 0.047 seconds. The contour plots will update automatically. To set the legend to show the overall maximum for the requested analysis time range and to see the animation, click Play. The maximum resultant displacement over the entire requested analysis interval, 0.035 seconds to 0.05 seconds, is 0.12 millimeter. Click Save and close the file. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about performing stress analysis in SolidWorks Motion. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module Exporting to FEA. Here are the key takeaways from the module. Click each tab to learn more. Here is a chance for you to practice what you have learned. Offline exercises are available for this module. To attempt these exercises, you must have access to a SolidWorks installation. To complete each exercise, download the self-extracting executable file from the e-course details page on mysolidworks.com. This file contains the sample models and exercise PDF file for every module in the e-course.